Hello students, welcome back to my chemistry lectures on thermodynamics. Today I'm going to talk about different types of enthalpy change. Different types of enthalpy changes. Or let me discuss about types of enthalpy changes. Types of Hello students, Hello students, welcome back to my chemistry lectures on thermodynamics. In this video, I'm going to explain or I'm going to discuss with you. Hello students, welcome back to my chemistry lectures on thermodynamics. In this video, I'm going to discuss about different types of enthalpy changes. Enthalpy changes I'm going to discuss. Mainly in this video, I'm going to discuss about enthalpy of number one is enthalpy of atomization. Enthalpy of atomization number one. Number two is about bond enthalpy. Bond enthalpy changes. So which is otherwise called, this is otherwise called bond dissociation. Bond dissociation enthalpy. Bond dissociation enthalpy. After this, the third one we are going to discuss about is lattice enthalpy. Lattice enthalpy change. Lattice enthalpy change I would like to talk about. The first, let us take enthalpy of atomization. So what is meant by enthalpy of atomization? Let us discuss now. So what is enthalpy of atomization? So enthalpy of atomization is said to be, so mainly this is applicable to elements. So elements like sodium or silver and even for molecules also we can apply molecules also. So what is enthalpy of atomization? Enthalpy of atomization is nothing but, so energy changes takes place. Energy changes that occur during change of an element to its gaseous free atoms, gaseous atoms, or conversion of molecules to its free atoms is whatever the changes takes place during the conversion of an element, solid element to gaseous atoms or molecules to free gaseous atoms. So enthalpy change is said to be what we call means enthalpy of atomization. This is said to be what we call means enthalpy of atomization. So enthalpy delta AT atomization, and if it is measured at standard conditions like 298 Kelvin and 1 bar pressure, then it is said to be standard enthalpy of atomization. So once again I'm defining what is enthalpy of atomization. The energy changes takes place or energy changes that occur during the change of an element, solid element. So state will be solid element to gases, free atoms, or conversion of molecules to into free atoms. So that enthalpy change is said to be enthalpy of atomization. If it is measured at standard conditions, then it is said to be standard enthalpy of atomization, we say. Generally, enthalpy of atomization values will be more in transition metals. Transition metals due to stronger interatomic interatomic forces between them. Indirectly, we can say stronger metallic bonds we can say. So if you take the diatomic molecules like hydrogen gas elemental form, so if you want to convert hydrogen gas into free hydrogen gaseous atoms in the form of gaseous state, the enthalpy of atomization for the diatomic molecule of hydrogen will be, so how much the value will be, so 435 kilojoules per mole. That means if you take 1 mole of hydrogen gas, molecular hydrogen gas, if you want to get 2 moles of atoms, free atoms, if you want to get, for breaking of these bonds between the hydrogen atom in the molecule, the energy change delta A, enthalpy of atomization, will be equal to positive 435 kilojoules per mole. We require the energy. So this energy is said to be enthalpy of atomization of hydrogen gas. And if you take for oxygen atom, so for oxygen atom, if you take oxygen molecules, one oxygen molecule, if you take 1 mole of oxygen, 1 mole of oxygen convert into 2 mole of oxygen atoms, free atoms, so gaseous atoms, if you want to convert 2 moles of gaseous atoms, if you want to convert, the enthalpy of atomization for the oxygen atom will be, standard enthalpy of atomization is equivalent to how much? So it will be 428 kilojoules per mole. 400. So sometimes the enthalpy of atomization is said to be, see, since between the oxygen atoms and between the hydrogen atoms, so what bonds are present between hydrogen atom? So covalent bonds are present. Covalent bonds are present. Covalent bonds are present. For breaking of this, if you want to make, this is a molecular form, and if you want to make free hydrogen atoms, if you want to break, So energy required because so between the two atoms there is interatomic forces are present. For breaking of these interatomic forces, energy required, that energy is said to be enthalpy of atomization. So this enthalpy of atomization, energy otherwise called, so energy required for breaking of bond, breaking of the bond. Hence this is said to be what we call means bond dissociation, bond dissociation enthalpy, bond dissociation enthalpy. So it is said to be bond dissociation enthalpy also we say. Now for molecule, if you take the molecule like CH4 is a molecule, gaseous molecule, and for conversion of CH4 molecule into so gaseous carbon atom, gaseous free carbon atoms, and 4 moles of hydrogen gaseous atoms. So the energy required, enthalpy of atomization of this molecule. So standard enthalpy of atomization of the molecule will be so 1665 kilojoules per mole, joules per moles it consumes. That means we need to apply energy for methane molecule. How much? So if you take 1 mole of methane to get 1 mole of carbon atom, free atoms, and so 4 moles of hydrogen atoms. So we require energy. That energy is said to be what we call enthalpy of atomization. Standard enthalpy of atomization will be positive. So 1665 kilojoules per mole. So here the energy that we supply, so for breaking up this molecule into free atoms depends on so strength of bonds present in the molecule. So hence, and this enthalpy change is said to be so bond dissociation. So enthalpy change, we say enthalpy, bond dissociation enthalpy change. As you know that during chemical reactions, so energy required, energy released, either energy absorbed or energy released. So that energy absorption and energy releasing only for breaking of breaking of bonds, and later making of new bonds takes place. While breaking energy is required, and for making energy is released. So during the chemical reactions, breaking up bonds takes place and making up new bonds takes place during a chemical reaction. During a chemical reaction, so or in reactants, breaking of the bonds takes place, and in the products, making of the new bonds takes place. So if the energy released is greater than the energy absorption, then that reaction is said to be what we call exothermic chemical reaction. So if the chemical reaction in which energy absorption is greater than releasing is said to be endothermic chemical reaction, we say. There are two types of thermochemical reactions. We can classify based on energy absorption and energy. So releasing. So one is exothermic chemical reactions where enthalpy change is negative, and so endothermic chemical reaction enthalpy change is delta H will be the positive. So the bond dissociation enthalpy, enthalpy change. So in diatomic molecules and polyatomic molecules, the bond dissociation enthalpy can be discussed in two types of molecules. Number one, diatomic molecules. Number two, polyatomic molecules. The diatomic molecules like H2, O2, Cl2, we can write. Polyatomic molecules like CH4 and C2H6, polyatomic molecules, or H2SO4, polyatomic molecules, we say. The bond dissociation enthalpy in diatomic molecules. So just now, as I mentioned, H2, if you take 1 mole of H2 gas consisting of the molecules, 1 mole of molecules, and for breaking of this 1 mole of molecules, 1 mole of molecules to get free hydrogen gaseous atoms. So bond dissociation enthalpy is equal to energy required is equal to how much, as I mentioned, which is nothing but so bond dissociation enthalpy of hydrogen, we can write hydrogen for 1 mole. Enthalpy change is equal to 435 kilojoules per mole, which is equivalent to enthalpy of atomization. Since enthalpy of atomization of hydrogen bond dissociation enthalpy so is equal, hence it is said to be bond dissociation enthalpy and enthalpy of atomization both are same. So enthalpy of atomization of hydrogen 435 kilojoules per mole. If you take another example, diatomic molecule like 1 mole of chlorine, 1 mole of chlorine gas molecular form, if you take, and to get to free chlorine atoms, so gaseous atoms, if you want to get, so and delta, so Cl bond Cl, so bond dissociation bond enthalpy of chlorine is equal to so around 242 kilojoules per mole, which is endothermic. So for breaking of chlorine molecules, how much 1 mole of chlorine gas consisting of 1 mole of molecules, and so breaking them into free gaseous chlorine atoms. So for breaking in one chlorine containing covalent bond Cl, covalent bond with Cl. So for breaking of this chlorine bond, how much 1 mole. So to get free chlorine atoms, energy required is 242 kilojoules per mole, which is said to be bond dissociation enthalpy of chlorine. So this is. And if you take O2 gaseous molecules for breaking two free gases, oxygen atoms, so bond dissociation enthalpy for oxygen will be almost all equal to 428 kilojoules per mole we can write. So the bond dissociation enthalpy depends upon nature of the bond and the size of the atoms also. It depends. So let us discuss. So bond dissociation enthalpy in polyatomic molecules. Polyatomic molecules. For example, I'm taking CH4 methane gas, 1 mole. I'm taking. So as you know that in methane, if you look into the structure, tetrahedral structure, around the carbon there are 4 hydrogen atoms are bonded for the carbon. So in this methane molecule, all the CH bonds, how many CH bonds? 4 CH bonds are present. The 4 CH bonds bond length and their energy same. If you observe the polyatomic molecules containing so identical bonds around the carbon, CH bonds, so their bond lengths are same and their bond energy is also same, but the bond dissociation energy, one bond to other will differ. So methane molecules, 1 mole converted into, so 1 mole of carbon gaseous carbon atoms and 4 moles of hydrogen gaseous atoms. The total energy required is, so CH bonds breakdown, enthalpy change will be, bond dissociation enthalpy, bond dissociation energy will be 1665 kilojoules per mole energy required. So here the bond means bond breaking between carbon and hydrogen differ from one bond to second to third and fourth. But so how we get this 1665? This is the total energy required for breaking up this methane molecules into free carbon atom and free hydrogen atoms. 1665. So why the energy differs from between carbon to hydrogen? So then if the number of bonds are more in the molecules, then we have to consider another term is said to be mean bond dissociation bond enthalpy, or we can write average average bond dissociation. So enthalpy we can write. So average bond dissociation enthalpy. So for example, for the CH bond, first CH bond breakdown, how much energy is required, and for the second one, how much, third one and fourth one. So then you can write all the four values CH bond enthalpy changes, 4 values. So if you take this is 1, 2, 3, 4, 2 and 3, 4, if you take divided by 4, then we will get average bond dissociation enthalpy. Let me write clearly this one. For example, in methane, how many bonds are present? CH bonds are present 4. So and 4 CH bonds are present. Delta CH bond 1. So plus delta CH2 bond is second delta CH3 bond plus delta CH4 divided by number of bonds, how many? 4. Then we'll get mean dissociation bond enthalpy, which is said to be average bond enthalpy we can get in case of polyatomic molecules. So why we have to use average bond enthalpy? Because the 4 bonds that are present in the methane, though they are same and having the same energy, but so enthalpy changes will be different. Can you guess why? Because electronegativity changes from breakdown of, for example, CH4 environment bond environment. If you make the first bond, then carbon electronegativity polarity changes. Polarity of the carbon or central atom, polarity of the carbon atom changes for every bond breaks. So first bond is quite difficult, second bond will be so difficult, and third and fourth one easy, like that. So this is mean dissociation bond enthalpy, or which is otherwise called so average bond dissociation enthalpy, we say. Average bond dissociation enthalpy in case of polyatomic molecules. So polyatomic molecules, it is similar to, for example, if you take H2O, 1 mole of water, 1 mole of water, if you want to make 1 mole of oxygen atom, gaseous atoms, and so 2 mole of hydrogen atoms. Then we have to use average bond enthalpy. Bond enthalpy is equal to, so OH bonds, how many are there? OH bonds, how many? So OH bonds, 2 are there. Then OA means delta HO bonds plus delta HO bonds 2 upon divided by 2, we can get average bond enthalpy for so water molecule, we can get bond dissociation enthalpy. So bond dissociation enthalpy, strength of bond, it depends upon strength of the bond, and number 2, size of the atom, size of the atoms. Okay, so now let me discuss about